Tonight on Nova.
Hey, beautiful.
Antarctica, a mysterious hole in the ozone layer over this frozen continent, has summoned an emergency expedition here to uncover its cause.
The actual size of it, could compare to the thickness of Mount Everest, the size of the United States.
Is it a signal that something is dreadfully wrong with the global ozone layer? Join us tonight as the mystery unfolds. The Hole in the Sky.
Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by the Johnson & Johnson family of companies, supplying healthcare products worldwide. And by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials.
Looking up from Earth, the sky appears boundless. A celestial canopy of peace and beauty, unmarked by human imprint. Viewed from space, the global atmosphere is eggshell thin, a delicate blue haze encircling the Earth. It is the domain of wind, clouds, the air we breathe, the roof of our world. Antarctica, the coldest place on Earth. Here, a mysterious change has been detected in a vital element of the atmosphere. A piece of the sky has vanished. This may be an isolated event confined to this remote continent, or it may be nature's first warning that man is changing the global atmosphere in ways that will profoundly affect all life on Earth. What is at risk is a form of oxygen called ozone, which makes up a fraction of a millionth of the planet's atmosphere. This invisible layer, 15 miles high, acts as a sunscreen around the Earth, our only protection from deadly ultraviolet rays. All life, save that in the deep oceans, has evolved under it. Scientists warn that ozone depletion would affect every nation on the globe, with major effects on human health, including higher incidence of skin cancer, cataracts, and depression of the immune system. Losses of ozone would affect climate, damage the growth of plants, and disturb the food chain. The hole in Antarctica's sky may be the first signal of a threat to the entire world. Bob Watson directs NASA's program of upper atmospheric research. He is at the center of an international debate about how to protect the ozone layer.
We can't change the rate at which ozone is produced, but we can change the rate at which ozone is destroyed. And so what we're worried is that we're slowly reducing the level of ozone constantly.
In the past decade, scientists have come to realize the Earth's atmosphere is changing rapidly. For the first time, waste from industrial activity may be altering climate on a global scale. By the end of the century, an unnatural shift called the greenhouse effect is predicted to make the Earth warmer than it has been in the past 100,000 years. The same man-made gases involved in greenhouse warming also affect ozone. Climate fluctuates naturally on a grand scale, so it is difficult to separate out changes which may be human-induced. Antarctica's ozone hole provides a natural laboratory for studying a dramatic change which may or may not be of human origin. Only since the early 70s has man been able to look at Earth from a global perspective, with satellites in space and high-speed computers on the ground. But neither a satellite nor a computer detected the Antarctic hole. It was first noticed by a little-known British research group led by Joe Farman.
We have been measuring ozone in Antarctica since 1957, and these are, in fact, the longest series in the southern hemisphere. We were, I suppose, like everyone else, looking for long-term trends, which were going to be quite difficult to find. And then suddenly, before our eyes, we seemed to see something completely different, a seasonal variation of depletion. And this was so unexpected that we really felt we had to make quite certain our instruments were in good order and calibrations were correct before we could announce this to the world.
Farman's data revealed that October levels of ozone over Antarctica had dropped 50% in less than a decade. His measurements came from a simple ground-based instrument.
If you have your hands on the data and if you're actually writing things down, you almost have a tactile way of acquiring information. You get a feel for it. There's an experience alone can do.
He found it strange that no one else had reported the ozone hole, and at first doubted his own findings.
At the same time, we knew there were satellites flying over the world which should be seeing this, and it was very important not to set them off on a red herring if in fact we were wrong. So we had to go back, we had to check all the old observations with the instrument and make quite sure there were no calibration errors.
Farman's findings opened an international investigation into one of the most puzzling mysteries ever to confront atmospheric science. But if Farman was right, why hadn't the global satellites seen the ozone hole? At the Goddard branch of NASA, scientists read the report and searched for evidence of the hole in the past 6 years of satellite data. Richard Stolarski.
When the British first reported the ozone hole over Halley Bay, we went back and looked at our satellite data, which comes in at the rate of nearly 200,000 data points per day. To me, the data is sometimes overwhelming. When the instrument was first designed in the 1970s, it was thought that ozone values as low as are now being seen over the Antarctic would not occur. And thus the computers which take this data and turn it into ozone values were programmed to simply drop values that low, assuming that they were in error.
NASA had programmed its computers to ignore what was most interesting. When they sifted through the past 7 years of Antarctica's October data, they found the hole. Shown here at the center of this projection, it is the size of the United States.
We could confirm their results and we could extend the picture so that we could see the entire Antarctic region. That allowed us to see that it was not just a phenomenon of Halley Bay, but that it was a phenomenon of the entire region, and it moved around and was not static.
During part of October, the hole hovers over the American Research Station at McMurdo Bay.
Scott, can you zoom in on McMurdo there? Looks like it's right on the wall of the hole again. The real issue here, I believe, is whether or not this is an isolated phenomenon specific to the region of the Antarctic, or whether it is some indication of a miscalculation on our part as to what models are saying about the globe.
Science has come to depend upon computer models to understand the atmosphere and its driving forces: the rotation of the Earth, clouds, wind, temperature, precipitation, and the mighty engine of it all, the sun. The atmosphere is a complex chemical factory. Models must simulate 200 known reactions, about 40 of which strongly affect ozone. The sun's ultraviolet light constantly creates and destroys ozone, which is a highly unstable gas. When molecular oxygen is struck by ultraviolet rays, its chemical bond is broken, releasing 2 highly reactive oxygen atoms. Each of these atoms joins with molecular oxygen, forming ozone, or O3. Ultraviolet light goes on to destroy its creation, striking ozone again. More molecular oxygen is formed, along with renegade single atoms of oxygen, which search for more molecules to destroy, including ozone. This pattern repeats over and over during the daytime, so ozone and oxygen are continuously created and destroyed. The relative amount of each substance remains the same, held in a delicate balance. This is how ozone works in most locations. But over Antarctica, the atmosphere is unique. Throughout the winter, which comes in July, August, and September, A high rotating mass called the polar vortex captures air in a kind of swirling chemical cauldron. The air inside this funnel gets cut off from replenishing global air currents. There is little sunlight during the long polar winter to generate new ozone, so the level remains the same. A month after the sun's return in Antarctic spring, the vortex collapses, allowing normal circulation to resume. In the last 10 years, the amount of ozone in the vortex has dropped a dramatic 50% below previous levels. No one knows why, but theories abound.
Since the original paper appeared in Nature, we've really had a very good time because we've had so little data to check ideas against. So everyone has taken the opportunity to wave their hands and produce all their pet ideas out of the cupboard and see if they can possibly be used towards this problem.
There are two sets of ideas, those that attribute the hole in the sky to natural phenomena and those that blame it on man-made chemicals. One natural explanation invokes wind dynamics, pushing ozone up through the vortex in a kind of fountain effect. Another natural theory blames volcanic dust particles from the eruption of Mexico's El Chichon in 1983. Drifting south to the pole, these particles may provide a surface for chemical destruction of ozone. A solar theory suggests that a chain of natural chemical reactions triggered by abnormally strong solar flares may be destroying ozone. This same theory cites strange nitrogen gases produced during auroras, disturbances of the Earth's magnetic field, which are common in Antarctica. The leading suspect on the man-made side is a class of chemicals called chlorofluorocarbons, or CFCs, known to destroy ozone in the laboratory. CFCs are used as solvents for cleaning computer chips, refrigerants for car and building air conditioners, both as coolants and insulation for refrigerators, and as blowing agents used to make styrofoam egg cartons and fast food packaging. Outside the U.S., CFCs are used as aerosol propellants for anything from foot spray to hairspray. The CFC debate began in 1974 when Sherwood Rowland and Mario Molina of the University of California, Irvine calculated that chlorine in CFC chemicals posed a threat to the ozone layer all over the world. CFCs can last for a century in the atmosphere. Once they drift up into the stratosphere, they are bombarded with ultraviolet light, torn apart, and chlorine is released. This chlorine atom steals oxygen from the ozone molecule, beginning its cycle of destruction by forming chlorine monoxide, or ClO. The sun also strikes ozone, leaving free oxygen, which collides with ClO, releasing molecular oxygen and free chlorine. This process may repeat up to 100,000 times for every atom of chlorine. The groundwork for this understanding was laid by chemist Sherwood Rowland, who pointed out that CFCs do not break down in the lower atmosphere, but survive to destroy ozone in the stratosphere. He has since become an activist for CFC regulation.
For a long time, the view was that if you put something into the atmosphere, it went away. And what we have found now is that it doesn't go away, it accumulates there. And it's accumulating very rapidly. And it's made it a very large-scale global experiment, an experiment whose end we don't see, and one experiment which we probably ought to be ending as quickly as possible. Get back to leaving the atmosphere alone.
A different analysis of the problem comes from DuPont, a major producer of CFCs.
I am very comfortable that based on our projections of the effect on the ozone layer of current levels of chlorofluorocarbons emissions and modest growth in those levels does not represent a threat to the health of our human race on out 50 to 100 years from now.
The one thing which the lack of comprehension of the Antarctic ozone hole shows is that indeed we understand very little about the atmosphere. We often congratulate ourselves on understanding a lot of it, but in fact we're really very ignorant.
The theory behind ozone destruction is well established, but is the global ozone layer in fact being depleted? Are CFCs indeed to blame? Perhaps the Antarctic hole will provide some hard evidence. In that hope, an emergency national ozone expedition is launched in August of 1986. 4 teams of scientists undertake a hazardous midwinter journey to McMurdo Bay.
I copied the relay through South Pole.
Halfway from New Zealand, the plane's wing ices up and the pilot is forced to turn back. The next day, they make it. It has taken 15 hours to clear the blowing snow off the runway. The plane must drop off its passengers and cargo and quickly take off again before it freezes. The temperature is 30 below. The expedition hopes to gather the hard data to answer questions both intriguing and urgent. Is the hole of man-made or natural origin? Is it the first signal that all is not well with the global ozone layer? Located on the edge of the Ross Ice Shelf, McMurdo Station has a winter population of 100 people. The 4 U.S. bases in Antarctica are coordinated by the National Science Foundation, which has joined with NASA, NOAA, and the Chemical Manufacturers Association to launch this expedition. Leading the team is Susan Solomon, a young atmospheric chemist from Boulder, Colorado.
Just getting a field experiment to work in Antarctica is a real challenge. The other thing that's challenging about the whole problem is that it's a mystery which has suddenly emerged, which we didn't expect, and which has caused us to re-examine everything that we thought we understood about atmospheric chemistry. I find that extremely exciting and challenging.
In the commanding darkness of late winter, Solomon uses moonlight to take the world's first polar measurements of chlorine and nitrogen compounds. These will help to prove or disprove the CFC and the solar theories.
How are your fingers holding out?
After this one, I'm going to turn it over to you. My fingers are getting kind of numb, holding still.
The team tries to capture the moon in a mirror and aim its light down a hole in the roof.
George's got it. You want to do the next one?
The conditions on the roof were extremely cold on many occasions. Temperatures could be as cold as minus 40, wind speeds of the order of 40 miles an hour. So it was very hard work staying up there for 10 or 15 minutes making an observation. What are we doing, a blue or a red?
This is a red, 20-second red.
Good. Well, when we first got here in late August, we observed ozone levels which were actually rather high, even though we were in the middle of the vortex. About 3 weeks later, we came back into the vortex and the ozone had dropped through the floor. It was lower than 200 Dobson units. And that was, at the same time, very frightening and at the same time extremely interesting.
The hole's rapid appearance suggests a chemical mechanism to Solomon, but she continues to gather evidence, now in October, using the light of the sun.
Okay, that looks good. Let's go ahead then. I guess we'll take a couple of blues, take 3 blues, and then a couple of reds.
Okay.
Incoming light carries a distinct signature of the atmosphere's chemical composition, revealing which chemicals have been encountered on the journey from the sun. Each molecule takes a characteristic bite out of the wavelengths of blue and red.
Oh, real good. 52,000 pounds.
All right.
If the vortex stays over McMurdo long enough, the expedition may be able to gather enough data to piece together this atmospheric puzzle. A team from the Stony Brook branch of the State University of New York searches for chlorine monoxide. Since there are few natural sources of chlorine, high levels of this molecule would strongly suggest that man-made CFCs are causing the hole. Bob DeZaffra and Phil Solomon, no relation to Susan, use a microwave instrument they built themselves. Phil thinks the ozone hole may remain unique to Antarctica.
Conditions in Antarctica are very peculiar in at least 3 ways. The air mass in the stratosphere over Antarctica is isolated for many months, it's dark for many months, and it's very much colder than any other place except the Arctic. The coldness probably produces clouds at altitudes where they're not produced in other parts of the world. All of these 3 phenomenon, combined with the fact that the ozone depletion is really only a springtime phenomenon and that there is a complete recovery, suggests to me at least that it may be a special problem to Antarctica.
DeZaffra and Solomon hope the chlorine monoxide measurement will deliver the definitive evidence on the controversial issue of CFC involvement. A University of Wyoming team launches a balloon-borne instrument to take the first direct measurements of ozone at various altitudes inside the hole. David Hoffman.
Flying balloons in Antarctica in winter is something we've never done before, and The temperature extremes, minus 40, minus 50 degrees, are very severe on both the balloon and the people launching it. The winds can be very high, which makes ballooning very difficult. So it was a real challenge to find out if we could get these balloons off. And also in the stratosphere, the temperatures are even colder, like minus 120 degrees Fahrenheit, and we had no idea if the fabrics in the balloons would be able to withstand these temperatures. The first 2 months went very rapidly. We were very anxious to get to work, and we did a lot of work. We were never bored at any time, and I really enjoyed it as compared to the summer period down here when there's so many people. It was much easier working with fewer people.
Liftoff is scheduled for 6 a.m. It's always a tense time just before the launch. The winds must be strong enough and traveling in the right direction so the balloon won't crash into buildings or telephone wires in town.
Hey, beautiful! Great, looks good.
The balloon detector will also count ice and dust particles, providing clues as to whether the volcanic or the wind dynamic theories may be correct. If the dynamic idea holds merit, Hoffman should see particles rising up through the hole in the fountain effect.
When people talk about an ozone hole, you would think of a hole bored down into the atmosphere, perhaps, where there's no ozone. And what we find is that it's not that at all. It's more like the shape of a wafer. And the actual size of it, could compare to the thickness of Mount Everest, the size of the United States.
Hoffman uses telemetry to track the balloon, which sends electronic signals to receivers inside this dome.
It's out of sight. It must be in the clouds. This is right at the base of the ozone hole. We're just getting into the region now where the ozone depletion has occurred. Internal temperature in the ozone package is 24 degrees, so it's nice and warm in there. The ozone pressure is now up to 50 nanobars, but these are very low values. And it's roughly half of what it would be at about 50,000 feet.
While the Wyoming team samples ozone directly inside the hole, a team from the Jet Propulsion Laboratory in Pasadena, California, takes measurements from the ground. This remote hut was built especially for their $3 million instrument.
I think this is all right.
Barney Farmer heads the research team running the infrared spectrometer, a version of which has flown on the space shuttle. Peering through a window directly at the sun, this instrument uses a laser to take precise readings of more than 30 different chemical molecules in the atmosphere.
I can't tell yet. The sun's not quite bright enough. What time does it rise today?
Let's see. I think it's just after 3 o'clock. That's 3:10.
Well, it gets earlier every day.
I know. Less and less sleep. More and more work.
I'm going to put heat on just for a few minutes, okay?
All right.
Well, the sun emits radiation over a wide range of wavelengths. We're concerned with the infrared part, which is the region of wavelengths just longer than visible radiation. As the radiation is transmitted towards the surface of the Earth, the atmospheric molecules remove rather specific frequencies. Each molecule removes its own radiation. And so we end up with a signature of the atmospheric composition. And this is rather like fingerprinting the atmosphere, so we have a simultaneous measurement of the whole inventory of species.
Because of the sophistication of their instrument, Farmer's team won't be able to look at their data until they get back to the computers in California. But ultimately, their work will provide the most comprehensive picture of chemical elements inside the ozone hole. New information on the position of the hole carries disappointing news for the Stony Brook team. Bob DeZafra.
I think the biggest surprise to everyone when we arrived here and began to see Dave Hoffman's balloon experiment results is that the ozone depletion is occurring at a lower level in the stratosphere than had been anticipated. That's particularly frustrating to our experiment because we're primarily sensitive to chlorine monoxide emission from the middle stratosphere, and what's happening is that if there is chlorine monoxide, it's going to be in the lower stratosphere. That poses a real problem for us to try to get the sensitivity needed to extract some information about that low layer of possible chlorine monoxide.
And so the ozone hole does not give up its secrets quite so easily. The Stony Brook team is cheated of its prize, measuring the kingpin chlorine monoxide molecule inside the hole.
Just in the context of this.
Once a week, the four teams gather to put their findings together. Tonight, they try to fit what they are learning day by day into existing computer models.
The problem that we're facing is that nobody has built a model that simulates these observations. For one thing, nobody knew about these observations until a couple days ago.
Within the group, there are strong disagreements over interpretation of data.
Simulates it. I don't think you can evaluate your data by comparing it against a model, unless you really knew that the model would produce it.
If we take what we heard from Dave just before, if it's 18 kilometers, 60 millibars, right now or in late September, that's fine.
But even at 18 kilometers, Phil, the depletion is dying out.
It's not dying out. He showed it. That's not what he showed at all, Susan.
Emotions run high, partly because of the expectation that these scientists will come up with a definitive answer on the cause of the
The data we
hole.
were looking at that I showed you came from right during the period.
Well, particularly when you're dealing with something as controversial as the ozone hole, the problem is that it cannot never be a purely objective judgment. So, of course, we've had disagreements, but I think those have been healthy. They've caused us all to think.
It soon becomes clear that another year of observations will be needed. Still, the expedition has learned enough to cast doubt on two key theories. As Susan's experiment showed, nitrogen dioxide levels are very low, ruling out solar activity. Dave's balloon found no evidence of particle uplifting. The fountain effect is not in sight, although other dynamic mechanisms cannot be ruled out. The altitude of the hole is between 12 and 20 kilometers, much lower than previously thought. The rapid appearance of the hole with the springtime sun suggests a photochemical process. Whether natural or man-made has yet to be determined. And what about chlorine from CFCs?
It could very well be that the ozone hole is caused by something completely different from what's been proposed so far, but based on the existing theories, chlorine is the only one we can't rule out. Until we've analyzed all the data, it's going to be very difficult to make any statement about chlorine.
Scientific caution sometimes conflicts with personal conviction. When is the evidence strong enough to take action? Given the stakes, Barney Farmer believes we have reached that point.
There's no question in my mind that we have a problem. Since the days over 10 years ago now, when we first measured hydrochloric acid in the atmosphere, in an amount that was almost exactly what you would expect from the destruction of the CFCs that we'd used up to that time, and then the hydrofluoric acid, and hydrofluoric acid, HF, has only man-made chemicals as its source. We've watched both of those species, those molecules, grow in the upper atmosphere to the point where they are today. It doesn't take a scientist to point out that we're doing something that we shouldn't be doing to the atmosphere and that we'd better stop it if we don't want a real problem.
Even if the hole remains confined to Antarctica, the region will be a test case of how ozone changes affect life. Many creatures live underwater, protected from ultraviolet rays. Birds may gain some protection from their feathers, but scientists have not yet begun to study what biological effects may happen here.
We don't understand the cause of the depletion of the ozone layer. If a change like that were to pop up somewhere else, it would be extremely damaging to biological life. If it's happening here and we don't understand the causes of it, how can we be sure that it won't happen somewhere else? So it's imperative that we do the most we can to uncover the cause so that we can understand whether it is something which is going to be restricted to Antarctica for the rest of eternity or whether it has some real implications for other parts of the world.
Joining a 3-month mission to Antarctica requires a certain kind of spirit and more than a few sacrifices.
I had to give up Monday Night Football.
We don't have any bathtubs in McMurdo, it's all showers.
I rather enjoyed it here. I might get in trouble when I get home saying that, but...
All right.
Meanwhile, back home in Washington, the press was poised and waiting for the latest news from McMurdo.
McMurdo, this is NSF Washington. This is NSF Washington. Do you read me? Over.
Excuse me, this is the Jerome operator. Would you please speak closer to your microphone in Antarctica?
I can't get much closer than I am. Can you hear me at all?
Roger, David. We're getting you loud and clear now.
The transmission was at times a little murky, and so was the message. The press corps looked puzzled, probably with good reason.
Could you tell us what your experiments have told you? Do you think that these chlorofluorocarbons are causing this depletion and the ozone hole that you are studying?
As I just said, we do not feel that we have established the cause of the hole at this time. However, we believe that a chemical mechanism is fundamentally responsible for the formation of the hole.
Dr. Solomon or anyone else who's there, many of us will be broadcasting to Americans all over America from the 8th grade on up. Could you possibly think in terms of instructing an 8th grader and describe your strong evidence against the proposed dynamical and solar models of the hole formation and define the dynamical and solar models? Simply.
Okay, let me just one more shot at it, maybe.
Some new ideas held more promise than others. While the expedition took observations at McMurdo, Jerry Malman of Princeton University was working up a new dynamics theory based on his computer model.
Modeling the atmosphere is an extremely difficult thing. Effectively, what we're trying to do is stuff the entire atmosphere into a computer. You think about it, that's really quite preposterous that anyone would even try it. But what's amazing is that we've had stunning successes, but we have a long, long ways to go. It's a hard, hard problem.
Which brings us to the story of the Chinese lunch.
Paper state.
Well, last spring I was at a scientific meeting on the Antarctic ozone hole, and a few of my chemical colleagues and I were arguing on chemistry versus dynamics. So just for fun, I offered them a bet that the ozone hole would actually get less deep this year. And two of my prominent takers were Susan Solomon and Bob Watson, and it looks like I've won the bet.
Latest NASA measurements reveal that both temperatures and ozone levels were up slightly in 1986. Malman claims this supports his theory for how dynamics may be contributing to the Antarctic hole. Malman's model holds that under normal conditions, atmospheric waves carry ozone and heat from the tropics to the South Pole. If for some reason these waves dropped off and temperatures fell, less ozone would reach the pole. Still, there is no explanation for why this may have happened or the speed with which the hole appeared. Malman himself admits his theory may require a chemical mechanism as well.
In my opinion, it's very common that unusual or singular events are often the result of a combination of improbable events. Every car accident you were ever in probably is in that category. Every hurricane, every severe storm, every hailstorm, every thunderstorm requires a confluence or superposition of unusual and somewhat rare events that add up to make a very impressive phenomenon. We scientists have spent a lot of time arguing with each other, is it chemistry or is it dynamics, and if so, what?
Pushing cookie?
Yes, please. And my suspicion is that after the smoke clears, that we will find that it indeed was a combination of chemistry and dynamics that really explained Antarctic ozone as it happened.
And what do computer models say about global ozone? If they fail to predict the Antarctic hole, can they still be trusted?
It's a good question to find out whether we believe in the models. We test them normally against the measurements of the normal atmosphere at mid-latitudes, and there they do a reasonably good job. They clearly have not done a very good job in the Antarctic region. However, that region may be very, very unique. We know it's dynamically unique, and it's got very unique radiation properties. And so just because we've failed miserably to understand Antarctic ozone doesn't necessarily mean to say that our understanding of the global ozone problem is equally as bad.
As perplexing as the Antarctic ozone hole is, the real fear is that it may be the beginning of ozone depletion all over the globe. The satellite has detected a smaller hole over Spitsbergen, Norway, near the Arctic Circle. There are also ground-based indications of possible depletions above Switzerland. These may be natural fluctuations, but they must be closely watched. At NASA, Donald Heath.
The satellite instruments now are telling us that the global levels of ozone are decreasing. These measurements only cover a 6-year period, so they really should only be taken as a warning. This is not a final conclusive evidence that man's activities are indeed destroying the ozone, but it tells us that ozone is decreasing and we may have a very serious problem in the future.
Over the past 6 years, an instrument aboard the Nimbus 7 satellite has shown a drop of 3% in the total amount of global ozone. But satellite instruments cannot be recalibrated in space and do drift in sensitivity. Scientists believe they have corrected for this drift. However, they are not entirely sure. NASA is now assessing the validity of its findings.
At this moment in time, there is no reason to believe the satellite data has been incorrectly interpreted. However, it is such a new finding with such importance that we just have to be especially careful.
The problem with finding a trend in global ozone is that ozone is not a steady quantity. If you look at the ozone, particularly over any point, you see that it fluctuates on all time scales, so that the ozone level may be going up and down daily, weekly, monthly, yearly, and in fact may have cycles of a number of years involved in it. So that picking out the trend is trying to see a very small slope in something that's actually going this way.
Definitive answers about global ozone depletion will require many more years of observation. The stakes are high, but so is uncertainty. The stage is set for a policy debate. At the World Resources Institute, Rafe Pomerantz.
When you talk about uncertainty, it seems as though we know nothing. But actually, if you listen, there are many, many things that people are very confident about. We do know that chlorine will destroy ozone in the stratosphere. We know that more carbon dioxide or chlorofluorocarbons or nitrous oxide in the atmosphere will warm up the Earth. We don't know quite how much or how fast, but we know it will occur. We also know that the levels of these changes going on in the atmosphere are very, very large.
What would life be like in an ozone-depleted world? If the ozone shield were seriously damaged, intense doses of the sun's deadly ultraviolet radiation could bring major increases in the rate of skin cancer. Dr. Darrell Regal.
In terms of skin cancer, there are certain things we can do to cut down our risk of developing this disease. We can wear sunscreens, which will protect us from the ultraviolet light that hits our skin. We can avoid the midday sun, which will protect us from the sun's strongest rays. And we can wear clothes that cover our skin, again to protect ourselves from damage. However, once the ozone layer is depleted, there's really not much more we can do to protect ourselves from the increased ultraviolet light that's going to be hitting the entire world, and the problem of skin cancer is going to increase.
For every 1% decrease in ozone, there's a 2% increase in the amount of damaging UV light reaching us. Depletion in ozone may also have implications for global food production. In an attempt to simulate an ozone depletion, Alan Taramura of the University of Maryland is blasting this soybean crop with artificially enhanced ultraviolet light.
Overall, plants are affected by ultraviolet light in terms of a reduction in the growth of the plant, and that includes a reduction in leaf area, or the size of the leaf, as well as a general stunting or reduction height of the plant. In addition, we know that ultraviolet radiation can affect the yield that's produced by the plant, as well as the seed quality. In one of our soybean varieties, Essex soybean, we found that a 25% ozone depletion results in between a 20 to 25% decrease in seed yield.
Large increases in ultraviolet light would also affect the ability of ocean plankton to reproduce. Since plankton anchor the sea's food chain, this could cause disruptions which would propagate up the chain. New studies show that higher levels of ultraviolet light increase hydrogen peroxide, a key ingredient in the formation of acid rain. The connection may stretch ordinary bounds of belief, but a trip to the beauty salon in Paris may contribute to Waldsterben, or forest death in West Germany. In a curious twist, ultraviolet light combines with car exhaust to create ozone smog, which causes major damage to crops, over $2 billion in the U.S. alone. Too much ozone on the ground, not enough up there. Maybe what the world needs is an ozone rezoning act. Unfortunately, it's impossible. Ozone plays a vital role in regulating heat in the stratosphere. Once it is disturbed, climate may change in ways science cannot yet predict. Better understood is the greenhouse effect, climate change on a grand scale. The same gases which affect ozone also accelerate this global warming. At the Goddard Institute for Space Studies, Jim Hansen's model predicts dramatic increases in temperature, which have already begun.
People often think that the greenhouse effect is something that will only affect our great-grandchildren, but actually it's a lot closer than you think. We expect that the temperature will have increased to a level which hasn't been experienced in 100,000 years within the next 10 to 15 years. And by the time we get to year 2030, which is 43 years from now, the temperature will be 4 to 7 degrees Fahrenheit warmer than it is now.
If greenhouse gases continue to increase, the world may warm 2 degrees by the year 2000, 3 degrees by 2010, and up to 7 degrees by 2030. In further predictions for the middle of the century, Denver may go from its current 33 days a year over 90 degrees to 86 days. Washington may jump from 1 month to nearly 3 months. Dallas may leap from 3 months over 90 to nearly half the year. Carbon dioxide from the burning of fossil fuels, nitrous oxide from automobiles, emissions from CFCs, and methane from farming all contribute to the greenhouse effect. These gases act as a thermal blanket around the Earth, trapping solar infrared radiation reflected from the surface. CFCs contribute 20% to greenhouse warming, second only to carbon dioxide. Michael Oppenheimer is an atmospheric scientist with the Environmental Defense Fund. He warns of major ecological shifts in the making.
The greenhouse effect will bring about the largest climate change in the experience of humankind, and it will happen in a quicker time scale than any other change in climate. We have no idea really what this will be due to the biosphere, but we can guess. Plants, animals are used to responding to climate changes that happen over the course of hundreds or maybe thousands of years. This change will happen in the course of 50 or 100 years.
Disruptions in agriculture and water shortages are predicted. With shifting rainfall patterns, the Midwest may return to the days of the Dust Bowl. Sea level is expected to rise 3 feet within the next century due to thermal expansion of the oceans. This may cause flooding of coastal cities and low-lying areas such as Bangladesh and Indonesia. There are long-range concerns about melting of the polar ice caps. Uncertainties are associated with all models, and exactly what will happen where remains in question. These dire predictions also leave out one factor: the human ability to change. The hole in Antarctica's sky, whether of natural or man-made origin, helped to bring a sober realization that man may be capable of causing dramatic changes in the natural conduct of the planet's atmosphere. Although conclusive proof is a long way off, a movement has begun even within the chlorofluorocarbon industry itself toward controlling these chemicals. Part of the reason is that CFC production is growing at 5% a year, and demand is on the rise. First invented in the 1930s, CFCs are safe, cheap, and efficient. The products they made possible became part of our vision of the good life.
You move in an atmosphere all your own, far above the crowd. The air you breathe is changed several times a minute without a window being open. Other cars you drive. This one, you Thunderbird.
Southern cities like Miami were able to grow and flourish partly because of air conditioning. When it was discovered in the mid-70s that CFCs might be dangerous to ozone, the U.S. unilaterally banned their use in aerosols. Companies soon came out with new environmental formulas propelled by hydrocarbons. In the meantime, CFCs have quietly grown again to the peak levels of 1978. The U.S. accounts for about 30% of CFC emissions worldwide. Major producers are DuPont, Allied Signal, Penwalt, Kaiser Industries, and Raycon. Until recently, the CFC industry has opposed any new regulation.
The industry point of view since 1974 has seemed to me that chlorofluorocarbons are like people. They should be considered innocent until proven guilty. And I don't think that that's the proper approach. What we really need to do is to protect the atmosphere and not the chlorofluorocarbon industry.
Historically, there's been a marriage of convenience between the scientists' tendency to say, don't ask me for a conclusion until the last results are in, and industry's desire not to have to make changes in the way it operates. So in the past, the industry has been using scientific uncertainty as an argument for delaying any regulatory action.
But last fall, the relationship between uncertainty and industry's position on regulation shifted dramatically. To everyone's surprise, the Alliance for Responsible CFC Policy, an industry coalition group, changed its mind. At a September press conference, President Richard Barnett.
Responsible policy dictates, given the scientific uncertainties, that the U.S. government work in cooperation with the world community to consider establishing a reasonable global limit on the future rate of growth of fully halogenated CFC production capacity.
Barnett is vice president of York Air Conditioning. He argues that the industry can do a lot to conserve CFCs on a voluntary basis through product leak testing and making sure that CFCs do not escape during the manufacturing process. At the end of a product's useful lifetime, CFCs could be recovered and recycled, instead of being emitted into the atmosphere. At present, there is no provision for such CFC recovery. In the fall of 1986, DuPont too changed its stance on regulation and called for an international limit on CFC growth. DuPont commands about half of the U.S. CFC market. The company had been at work developing alternatives, but in 1980, when the regulatory climate quieted down, it shelved its research. Existing alternatives are not only more costly, but in some cases flammable, corrosive, or carcinogenic. The company now estimates it would take 5 to 10 years to complete toxicity testing on possible alternatives and to bring new products to market. Without the threat of regulation, however, DuPont frankly admits there is no incentive to take these steps.
It may require regulation to bring about alternatives, or the threat of regulation. If we go back in history, you'll find that in the mid-70s, when the chlorofluorocarbons ozone issue was first elevated and the threat of regulation to aerosol producers was announced, the aerosol producers moved away from chlorofluorocarbons long before the regulation was put in place. So a threat of regulation may have the same effect at this time.
Protection of the ozone layer is the legal responsibility of the Environmental Protection Agency. In May of 1986, David Doniger of the Natural Resources Defense Council took EPA to court to force it to move faster on the issue. Administrator Lee Thomas.
Well, I don't think it took the lawsuit to get us there. I think the lawsuit, and we have a lot of lawsuits, certainly focused attention in the agency on time frames for making decisions. The agency, I believe, was moving in the same direction that the people who brought the lawsuit wanted us to move in. But I do think the lawsuit contributed to us making decisions very concretely about the time frame within which we were going to do that.
EPA must decide by November 1987 if the risk to ozone warrants further CFC regulation.
The U.S. can provide a leadership position today, just as I think it did back in the late 70s. In 1978, we banned all aerosols with CFCs because of our concerns about ozone depletion. Today, we're going into an international negotiation proposing a very strong position on dealing with this issue of ozone depletion in the future. I think there's also the potential for us looking at what we can do domestically and what we can do with export and import controls to deal with the issue as well.
Environmental groups argue that the U.S. could take unilateral action, perhaps by restricting the import of cars using CFC number 12 in their air conditioners, or computer chips cleaned with CFC solvents. But U.S. industry is adamant that any regulation should be global.
There is no way that we can solve a stratospheric problem by taking a unilateral action in the United States and have chlorofluorocarbons production and emissions continue to grow around the world. It all ends up in the same stratosphere. As a result, we have to approach the problem globally.
Geneva in December 1986. The United Nations Environment Program convenes a negotiation on an international global ozone agreement.
We are here today because we recognize that urgent action is necessary to prevent destruction of the atmosphere's protective ozone shield.
The U.S. delegation proposes to freeze CFC production at current levels and to phase out certain CFCs within 10 years.
The international agreement, which we hope to achieve in the negotiations beginning here this week, would serve in effect as an insurance policy to protect future generations from the damages that we see occurring to the ozone layer and from the resultant effects on human health and ecology.
The U.S. position was greeted coolly by industry observers. John Mills of Imperial Chemical of England.
There is no environmental case for limiting CFC emissions to present-day levels. We believe that production limits could be set at a level which allowed industry the time to develop the necessary alternatives and for those to be evaluated by the user industries.
If an agreement is made, it will be decided by delegates from nations. The European Economic Community has been most conservative about taking any action. It has yet to ban the use of CFCs in aerosols. Japan has also been slow to move toward regulation. CFCs are used heavily in its automotive and computer industries.
Climate will change. The only uncertainties are when and by how much. The type of protocol we agree will be a determinant in this equation.
I'm optimistic for the first time in many years that we can reach an international agreement. Industries and governments seem to be taking a much more flexible approach this year than they did even 1 year ago, let alone 2 years ago.
An informal consensus was reached at Geneva that production of certain CFCs should be frozen at current levels. But a binding international treaty may be years away. Meanwhile, science does not provide answers according to society's timetable. There is no final word yet on the cause of the Antarctic hole. Further analysis of the National Ozone Expedition's data may provide more clues as to the cause. A second expedition is planned for next season. With risks and uncertainties both so high, scientists have been unusually forthcoming about their personal views.
Well, I think myself that we should look on the Antarctic ozone hole as nature's way of giving us a gentle warning on a rather restricted temporary stage. Until we know that this is some natural phenomenon, we should heed that warning and take some action to at least reduce the use of chlorine-containing chemicals.
It's quite obvious that people will have to be licensed to put things into the sea or into the atmosphere in the future. It should be just like the pharmaceutical industry. It should be up to the releaser to prove that something is safe and not up to the scientists to prove that it's dangerous.
Society certainly can't trust the models to provide a definitive answer which will enable them to quantitatively regulate the CFCs. But what I think is significant is the fact that the models were taken by surprise. The fact that we can fail to understand the ozone layer so completely that we've seen a 50% depletion that we don't understand has to be an indication that we need to consider very carefully what we're doing to this planet, in my opinion.
There will always be something more to be learned by studying it for another 3 or 4 years. Primarily what we're learning now is that the ozone is going away, and it's time to act on what we already know.
This is an issue that affects not only us, but our children. We should be concerned today. If we put large amounts of CFCs into the atmosphere, if they were to have an adverse effect on either the climate system or the ozone system, once we've recognized that concern, it would take decades to centuries for the system to recover. Therefore, we can't simply say, let's put off decision making for another decade or so, insofar as if we do get a problem, that problem will last for centuries.
Science cannot tell us for certain if or when the global ozone layer will be depleted. It has told us that CFCs remain for a century in the atmosphere, that they can destroy ozone, and that they make a substantial contribution to global warming. It is up to society to weigh these known risks, to search for a better understanding, and finally to decide if and when this global atmospheric experiment should cease.
For a transcript of this program, send $4 to NOVA, Box 322, Boston, Massachusetts, 02134. Please be sure to include the show title. To purchase film or video copies of this program for educational use, call toll-free 1-800-621-2131. In Illinois or Alaska, call Collect 312-940-1260. This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for NOVA is provided by this station and other public television stations nationwide. Additional funding was provided by Allied Signal, a technology leader in aerospace, electronics, automotive products, and engineered materials. And by the Johnson & Johnson family of companies, supplying healthcare products worldwide.